All right, recording is rolling. Welcome to Monday, October 9. So, a few school things. You guys know that first 9 week ends in a few days. Check, focus, make sure that you've turned everything in. You don't see anything that says not turned in. No, you guys I haven't given you guys your dynamics quizzes back yet. I'm still waiting for a few more to come in. There's just a few more, right? But then hopefully get those back to you guys pretty soon. So you use corrections if you want. Right now, so context to what we're in the middle of right now. Last week we were doing this rotational type motion. We looked at rotational kinematics, had the turntable. You guys did Centripetal force lab, which we're about to score here. That's part of Unit 3 by AP's book. The other half of Unit 3 is universal gravitation. We'll start that probably a couple of days, and then put those two ideas together, make orbits, right? Gravitation plus rotation. Oh, I've got some orbits going on, right? Right. AP Classroom Unit 3 multiple choice questions have been open for a while. Let's have those due about a week from now on Tuesday. You guys know we have a 3-day weekend coming up, right? And then when I see you guys on Tuesday, I think you guys should have enough knowledge by then. I went read the questions myself, double checked. So, okay, yeah, I think by the end of this week, you guys should be able to answer those questions. Go over the answers then. All right. So here, let me throw this question up here. How do you guys think about this, and then we'll score these AP style write-ups back from last week, and then come back and touch on those. Right. So when we started this rotational motion stuff, I threw some examples to you guys, and one example was we're looking at this video clip from a movie called 2001: Space Odyssey. It's from the 1960s. They had this giant space wheel that was rotating in space. Right now, if it wasn't rotating, it'd just be floating around like an astronaut. Right? If it is rotating, you could like walk around on the inside wall. In fact, if it's going really fast, like a centrifuge, you probably feel really heavy. Right? But I wonder how fast you would have to rotate so that you felt like you were walking around the inside with like Earth gravity. Ooh, could you target like 9.8 meters per second squared? You could, right? Something like that. Probably has to do with something about how big it is, right? So hold on to the idea because we're going to come back to that. All right, so you guys ready to score these labs? Score these labs, right? Right. So it's kind of related to this lab right here, right? There's some similarities and differences. Right, here's what you guys found back last week. I split you guys up into 3 experimental groups. You're saying what force, in this case, provided by tension of the string, which is also equivalent to saying weight, right, would hold this mass swinging around in a speed, some speed along a curved path with this radial size, like right, the circle radius, right? So it's 4 variables juggling. Right? At the end of the day, put 3 different experiments together, and you guys found this out. Right now, it had to be 3 different experiments, so we could do some control, some independent variables at a time. Show you guys just one of the examples. Some of you guys were testing, let's say, these 2 variables, right? So independent variable, dependent variable, and then this was controlled, and this was controlled. Okay? All right, so V versus M, look inverse type to reciprocal, and then it kind of straightened out, but it still looks like a kind of a square root, right? Then squared the V, so V squared versus 1 over M. Ooh, and that was a direct relationship. So V squared is proportional to the reciprocal of the mass. That is consistent with this right here. Okay. Anytime 2 variables multiply together, some kind of inverse relationship going. Okay. There were a couple other perspectives too. We could put this whole formula together. Okay. All right. So you guys got your lab write-ups out? Because we're ready to score these things. Right, gonna have you guys score yourselves out of 12. I try to make it as close as I could to like what an AP rubric would look like. Right, so here we go. I split you guys up by cards. If you had the spades, that's the middle section. That's the relationship between the speed and the swinging mass. That looks like the graphs I just showed you. Right? If you had the diamonds, you're doing speed versus the hanging weight, and the hanging weight was equivalent to the tension, which was like the centripetal force. Right? And then if you had the clubs, you're doing V versus R. So you change out the radial size. So how's that? Right? So first 3 points, everybody gets the exact same first 3 points. Actually, these all start out the same type way, right? The scale to measure like masses and weights used I listed it earlier here, but really you guys use a meter stick, right? So meter stick and then a stopwatch, right? So you guys got scale, meter stick, stopwatch. You guys got those 3 measuring tools, right? This whole lab with those 3 measuring tools. Okay? The setup was the same for everyone, right? It says some version of put a string through a plastic tube, secure a safety bucket to each end of the string, whirl 1 bucket, which is the swing mass, in a horizontal circle so that the weight of the other bucket, the hanging weight, provides a centripetal force well, really it's the tension of the string, but it's equivalent to that, right? That holds the swinging bucket in a circle of constant radius, right? So 1 point for basic lab setup. Okay, let's get that. Then, which might look kind of like here. It phrased a little bit different here, but back on, well, last week I showed you guys a different version that I whipped up in like 2 minutes, right? Connect 2 canisters, blah, 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 through a pipe, swing a horizontal circle, blah, blah, right? Anyway, okay, so some kind of procedure. And the first step is just basically describe the setup. That's what we just look at. Okay. Okay. Then what? Okay. Measure. Right. They always want to know what variable are you measuring with what tool. Right. So I think this part was also the same for everyone. Measure the swinging mass with the scale. Measure the hanging weight with the scale. I mean, one would be in like grams or kilograms. The other could be in like millinewtons or newtons. Right? Measure the horizontal, sorry, the radius of the horizontal circle with the meter stick, right? Okay. So 1 point for use of the scale, 1 point for use of the meter stick. Okay. Next step is also the same for other groups. With the stopwatch, time 10 revolutions and divide by 10 to determine the time period of 1 revolution. So 1 point for use of the stopwatch, right? So got each tool and what you use, what you measure with it. Right? Everybody also did this next step. Speed is distance over time. So distance could be 1 circumference around the circle, and that would correspond to exactly 1 time period. All right, so 1 circumference divided by 1 time period, 2 pi divided by t, right? To determine the speed. Right? You could say speed. You can also say tangential velocity. Right? I want to be careful about just using the term velocity because the velocity changing because the direction's changing, right? Not the speed's changing, right? But the direction's changing. Right? So speed or tangential velocity. Right? Now, how I routed everybody to this was everybody related to b squared. So at some point you probably have like square the speed. Maybe that's like part of your analysis is kind of getting into, right? Repeat the previous few steps 3 times to find an average speed, right? That's always a point in AP's book. I think I may have listed them in a little bit different order, these steps, the example I showed you guys last week, but there's always a step for like multiple trials to just do the same thing over and over and take average, right? Sometimes you might want to include like to reduce experimental error or something like that, right? To reduce random error, right? Sometimes it'll be a little faster, so the stopwatch, right? And then all right. Here's where things get different. Right, you have to somehow at some point identify what your controls are and what your independent variable is. Right, and here's where each team had something different going on. Right, so if you have the spades, you might say something like repeat steps number through number for various values of the swinging mass. Right, there's your independent variable. Right, keeping the radius and the hanging weight constant. Okay, so you're identifying what's your independent variable, what's your controls. If you had the diamonds, you were repeating blah, blah, blah steps for various values of the hanging weight. So there's your independent variable, the hanging weight, keeping the swing mass and the radius constant. So there's your controls. Again, a point for identifying what's the independent variable, what's control. If you had the clubs, you repeat these steps above for various values of the radius. Right? So small radius, big radius, different radius. Keeping the 2 canisters the same. Right, you guys get that? All right. So a bunch of those steps are the same. That point it got a bit different. All right. So that was the procedure. The procedure is basically just gather the data. Right? What's your independent variable? What's your controls? Right? What tools did you use to measure what? Right. Now we're into analysis. Now, depending on what kind of lab you're doing, analysis might be different things. If I want you to solve for something specific, like a few weeks back, you guys saw what is the blast speed of the launcher. Right? You might want to break out some equations. And analysis could be, just break out equations and solve stuff, right? For something like this, where you're trying to solve what is the formula for centripetal force, you're looking for relationships among variables. So you want to break out graphs, right? You're looking for properties of graphs. Of course, that's what we did, right? So analysis is graphs in this case, okay? So for spades, what it came down to was b squared versus 1 over m. That was the most complicated one because it was like 2 steps away, right? That was this one here that I showed you guys, right? B squared versus 1 over m, because that was a direct relationship. B squared versus 1 over m, right? If you had the diamonds, it was b squared versus the hanging weight was a direct relationship. And if you had the clubs, it was v squared versus r was a direct relationship. Okay. And then, okay, so for each of those graphs, the slope is constant. Direct relationships. Okay. At conclusion, okay, there's of course 3 different conclusions. Right. So, do you guys know the story of like there's like a bunch of blind guys who are trying to describe an elephant? You guys ever heard the story? Right. So nobody knows what an elephant looks like, right? And they go through and they ask each guy, and each guy is like feeling a different part of the elephant. So one guy says, "Oh, an elephant's like a tree because it feels like a tree trunk," and he's like holding onto the leg, right? No, so no, it's more like a rope. And he's like pulling the tail or something, right? And everybody feels something different about the elephant. Okay. Well, that's what like you guys with this lab, right? Everybody has a little bit different perspective, and we can put all the perspectives together and get like, oh, okay, now we know what an elephant looks like. It's got this, it's got this, it's got this. Right, so if you had the spades, you guys figured out that the speed squared is proportional to 1 over the swing mass. If you guys, if you had the diamonds, you figured out that v squared is proportional to the centripetal force. And if you had the clubs, you figured out that v squared is proportional to the radius, right? Now, you put those 3 stories together, v squared is proportional to something on all those 3, right? Then you can get v squared is proportional to force times radius divided by mass. Then rearrange that, and you get forces mv squared over r. Well, a proportionality, but it turns out it actually is equal also. Right? So you guys figured out centripetal force is mv squared over r. Right? Oh, here it is. Looking for what is here. All right. So do you guys score yourselves out of 12? You guys scored yourself out of 12? Right. So just before you walk out of class today, just turn that in the grade tray, and then I'll just point the points in the grade book. Okay. You guys get there? All right. So this is good for here. If there's like a point mass on a string going around the circle, say, okay, I'm thinking about centripetal force. Force could be mv squared over r. Right? That's the force that's causing a change in direction. Notice it's not speeding up or slowing down, but it is a change of velocity because it's change in direction. Right? Oh, what about if you divide by this mass? Wouldn't that represent like centripetal acceleration? Right? That's what this bottom box is right here. Right? Which is actually what AP gives you. If you look at AP equations that you're allowed to use on the exam, the first 3 are the 3 kinematic equations. Then goes Newton's second law of motion. Then one to do with friction. And then, the 6th one right here, it says centripetal acceleration is v squared over r. That's that one right there. That one right there. Some speed, some radius of curvature. There's an acceleration associated with that. Okay. But what about, this away. What about back to this O'Neill cylinder? So now we're up in space, and we got this giant platform that's rotating, right? And what about if there's a ladder going across the diameter, and now one of these guys who's walking around on the outside decides, hey, I'm gonna climb up that ladder. It climbs to the middle. Right? Let me bring up the big version of this. The big version of this is it's easier to see. So there it is, just bigger, right? Right. So these guys are all walking around the inside. Right? If this thing's big enough, it might be hard to tell that they're not in an actual gravity field, right? If it's big enough, right? Now, if it's kind of small, then the Coriolis effect might be pretty dominant. Like, ooh, it's pretty wonky physics. If we're like throwing baseballs back and forth, like there's something off here, right? But if it's big enough, right? Right? But here's this guy. He's gonna climb this ladder, and he climbs it all the way to the middle, right? So now he's hanging out right here in the middle. You see this along this axis of rotation. This whole thing's rotating around this dashed line axis, right? What does this guy feel like right at the middle of this whole thing? Weightless. You're right. In fact, if you gave a little push off and then let go, you just kind of like float off into space, wouldn't he? Right? Yeah, you're like weightless right at the middle. But suppose he doesn't do that because he likes living. So he goes ahead and climbs back down the ladder. Ooh, does he feel heavier as he goes down? Ooh, right. Now that what's interesting about this is that his linear speed is changing at every single point, at every single rung on the ladder. Right? Like if there's some guy like hovering over here, it has a radar gun pointed at this whole situation. So it reads 0 meters per second there, and then point the radar gun. You point the radar gun at different places, you get different speeds. And all along, it goes faster, 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 faster. Right? But you know what is constant for this whole O'Neill cylinder? Is not the linear velocity, but the what? Yeah, the rotational velocity, like the angular velocity, like the turns per time. We might say revolutions per minute, but we're gonna call it like radians per second is the unit, right? So let's go back and do a little review from last week, right? So linear stuff, rotational stuff, right? So maybe if you want to figure out something about how fast you have to spin it, maybe that could be one of the questions, right? How fast does this thing have to rotate? That's like an angular velocity question, not so much a linear velocity question, or right? Like you guys were working with linear speed in your lab, but this whole like rotating disk, right? Maybe rule of thumb is like anytime you see like a platform rotating, like those rotating turntables we had last week, right? Or in this case, a O'Neill cylinder, right? It's probably easier to sort of solve it in terms of this angular velocity, right? So what we're about to do here too, right? You know what? There is a connection between linear speed and angular speed, right? And it's just you multiply by your radial distance from the center, right? You guys remember last week I had these Roosevelts on the turntable, right? Like if there's one in the middle and then one near the edge, right? Give this thing spin. This guy in the middle, where's he going? He's not going anywhere. It's just like it's getting dizzy, right? That's about it. But like the further out you are, aren't you moving faster, 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 and moving further, right? Right. Circumference equals 2 pi r. What's the version? Okay, so all that, right? Right. So hey, how about like the guy on the O'Neill cylinder like climbing down the ladder? Ooh, that's kind of like the same type thing, right? So what about all the people on the edge? All the people on the edge, you probably want them to experience 9.8 meters per second squared. Hey, maybe I should take this expression right here and substitute it in for your guys' centripetal force formula. You guys think I should do that and see what happens? Centripetal force maybe for like a turntable situation? Let's check it out. Okay. So you guys got last week centripetal force is mv squared divided by r, but I'm going to say v is omega times r. Take that and substitute right there. That's what I'm going to do. Right. So centripetal force for like a turntable scenario. Okay, so mass is there. I got omega times r right here. I'm going to square that and then divide by the radial size. Yeah. Ooh, that r, that's the same r, right? So square on top, then divide one of them out. And I get centripetal force is m omega squared times r. Would that be centripetal force for like a turntable, right? It's expressed in terms of like angular speed. So something to do with that, right? Okay. Now, and if I show you guys the full poster, there's the full poster. Okay, there it is right there, right? Divide by the mass. All these people walking around the edge might have different masses. Maybe that guy's 50 kilograms, 60 kilograms, 70 kilograms. If you divide by their mass, then they all experience like the same like fake gravity, right? Just going from here to here, just divide by the mass, right? Right. Some of this kind of interesting here is if you compare these two, right? Your lab version versus like the turntable version, put them side by side, right? Now this one you have to think real deep on, but I'm going to throw you something to you guys that's going to look kind of paradoxical, right? In terms of your lab version with the point mass on a string, the centripetal force is proportional to the, well, it has an inverse relationship with the radial size, right? But on a turntable, you think in terms of angular speed, the centripetal force is actually directly proportional to the radius. Ooh, so that's kind of interesting. Right? Different kinds of speeds, though. Right? So have fun thinking about that one. Makes sense if you think really deeply about it, but really deeply about it. Right? And so how about back to this question then? What's the time period for one revolution so that everyone out on the outside experiences 9.8 meters per second squared? Okay. Maybe we should first solve for this omega, right? Like how fast is this thing rotating? You guys think? All right, so there we go. I'm going to start solving this. You guys in your notes, see if you guys can beat me to the answer on this. If you beat me to the answer, then it's a good indication. You know what's going on. All right, so I'm going to solve for that first. Maybe I'll pick up from that. Here, let's go. Centripetal acceleration for a turntable or O'Neill cylinder could just very simply be omega squared times r, right? How fast is it rotating? Right, square that times radial size, right? And maybe I have a target value for this, and I could also figure this out pretty fast. And I'm solving for how fast is it rotating. Solve for that, right? Okay. Here. I should just solve this in terms of variables. Right? But if you want to see like numbers side by side, we all do like a side by side, right? In terms of variables, okay, divide the r over, so omega squared is equal to centripetal acceleration divided by radius, right? Or with numbers here, I'll have 9.8 meters per second squared equals omega squared times. Ooh, guys, what is the radius? If the diameter is 1 kilometer, what number should I be typing in for the radius? Huh? Wait, what? Okay, 0.5 kilometers. No, do I want kilometers in my 500 meters, right? 500 meters, right? So I gotta have base SI units, right? Right. So let's go, yeah, because my gravity field, look, is meters per second squared. So I better have something to do with meters over here, right? Otherwise I mix in meters and kilometers, like, right. So let's go 500 meters is what I gotta have, right? So then omega squared would be 9.8 meters per second squared, all divided by 500 meters, right? The meters cancel. You could also call it meters per radius, so that radians comes out in the end, like that, right? Right. Square both sides. So in terms of variables, it's going to be like this right here. Okay. And then with numbers, say meters per second squared, meters per radius, whatever you think of it. Something like that. Okay. Something like that. All right, let's check this out. So square root, there's my gravity field. There's the radial size of this thing. Okay, and we're getting a numerical answer now. Okay, I'm getting this number on my screen. 0.14. Okay. Guys, that's 0.14 what? Huh? What? Radians per second, right? Radians per second, right? Because we got an angular velocity here, right? How fast is this whole thing turning? Right? Radians per second. Remember last week I made this whole deal about if you're ever dealing with any kind of angle or angular motion, in this case angular velocity, right? And you just have equations. There's no sine, there's no cosine, there's no tangent. What naturally falls out of the math is always going to be some version of radians. In this case, radians per second, because it's a angular speed. Yeah, right. So that's how fast this thing is rotating, right? Right. Okay. 0.14 radians per second. Remember, I wonder how many degrees per second that is. Guys, how many degrees in a radian about? About 57 point something? Okay, let's just do ballpark. Right? 0.14 radians per second. Every radian is about 57 degrees. Right? So, that's about 8 degrees per 7.98. Can I call that about 8 degrees per second? Right? If you like that, 8 degrees per second. Okay, so if you're off in space, watch this thing rotate. Yeah, I bet you can see it rotating, right? Rotating real slow, right? But you can probably see it. But that wasn't the question either. The question was actually how much time would it take to rotate once, right? Time to rotate once, right? Now I could think of 2 ways to finish this off. One way is you could do like distance equals speed times time, right? And the distance could be 2 pi radians. We're talking about an angular displacement, right? 2 pi radians, right? And the angular speed is this number, so you could solve for the time that way, right? So that's one valid way to do it. I'm gonna do dimensional analysis type. So this is a different way to think of it. It'll also lead straight to the answer. Suppose I want 1 revolution, because the question is how much time for 1 revolution, right? Well, we can just do some conversion factors, right? So what's my next step? What per what? 1 revolution. 2 pi radians, yeah. There's 2 pi radians is equivalent to 1 revolution. Right. Okay, so I know how many radians this thing's turning. What's my next step? Yeah, radians per second, right? Okay, yeah, 0.14 radians per second. Does the number 0.14 go on top or bottom? Yeah, bottom. Yeah. 0.14, right? Because I need the radians here and the seconds here, right? So that radians cancels out and I have seconds in the numerator. Right? So now I know how many seconds it's going to take, right? If it was a lot of seconds, maybe I could do another step, say how many minutes, but we don't need to go that far. Right, so it's 2 pi divided by 0.14. I'm looking at 44.9 seconds, right? You call that about 45 seconds. So someday in the future, I don't know, maybe 100, 200, 300 years from now, right, we get enough material in space, maybe we'll build one of these O'Neill cylinders, maybe, say it's a kilometer in diameter, right? You could pretty well predict it's going to take about 45 seconds to turn around once, because that would correspond to like Earth gravity, like on the inside, right? Which is probably like healthiest for like people walking around, kind of evolved to be in Earth gravity, right? That's right. Right? Hey, guys, good day. All right. Let's do some textbook questions. Or no, wait, right before textbook questions. Let's look at the rest of these posters. I think I may have flashed them in front of you guys once last week real fast, but here. Huh? Yeah, that's for my honors classes. So it looks like. Does does everybody here have the have these from chapter 7 puzzles? Right here. So I'm about to pull these out here in a couple minutes. Right. Oh, here. All right. Yeah. All right. So everyone see some. Got some right here. Puzzles. Right. So we'll look through those pretty soon. Right. Let's just look through a few of these posters. Right. So how about disorder? Right. And okay. Let's do this. Okay. So we just solved a whole problem with O'Neill cylinder, right? Okay, so you can figure out what's centripetal force, centripetal acceleration in terms of angular velocity, okay, something like that. Makes it directly proportional to the radial size, right? You walk up and down this ladder. Okay? Here's the original place where you guys started, right? So you guys did this lab and put together an squared over. Right? Now, if you think about it, there was a simplification. I mean, there was a little bit simplifications in the class. One of the simplifications you guys made is that can this can this string right here, you guys see this green string? Can that string be truly horizontal? No, because this swinging mass also had some weight, so it wasn't kind of pulling down. And the string didn't only provide a centripetal force; it also had to hold up the weight of it, didn't it? Right? No, it really didn't make that much of a difference. I worked at the math in my honors classes because they had a similar type question going on. It changed the answer by like 1 or 2%. So it, kind of negligible difference, right? But if you had a heavy enough mass here, or if you're swinging around slow enough, it would probably look more and more and more like a cone, wouldn't it? Right? Now, if you guys had a real flat cone, again, like take a like cosine of a small angle, and it doesn't really change it that much, right? But something like this, right? More and more of a cone shape. I've seen AP ask questions specifically about this. So let's look at this. What's going on? What's more accurately going on, right? So here's your point mass going around, like the swinging mass, right there. It's got two forces on it, two forces, right? There's this weight pulling down, which you guys kind of ignored last week, but that's okay. And then the tension doesn't really pull horizontally. It actually pulls like horizontally and also vertically, right? Has to do both, right? Those are the two forces, one down and one up to the left, right? So that there is a net force on your swinging mass. Of course there is. It's on a curved path. It's got to be a net force, right? But this tension pulling up to the left, well, it's doing two things. If you break it into components, right? Notice I've got this angle with respect to the vertical. If you break that into components, then it's pulling in, but it's also pulling up. And doesn't that up part have to match this weight acting down? Can that be true? Right? This up and this down have to balance it. Hey, that's what that says right there. Look at that, right? This is the sum of the forces in the vertical goes to 0 because this point mass is not moving up or down, right? So that has to be true, right? That's vertical right there, right? What about horizontal? Now, horizontal, there is a net force. Do you guys see it's this tension times sine of this angle will tell you this net force right here, right? Oh, that's what that one is right there, right? The tension times the sine of the angle is the net force, right? Guys, right. And furthermore, you guys know from your lab that net force is mv squared over r, right? Guys, that too. You could have these. Remember, there's really two forces on this guy. So you could have these tip to tail. If you take this guy and slide it down, tip to tail with this guy, oh, it gives you the net force right here, resultant. Or alternatively, if you take this weight and slide it up tip to tail with this guy, oh, you get the same thing. There's your resultant net force, right? Which is mv squared over. Mv squared over r is like the net effect. It is like the net force, which actually moves this on a horizontal circle, right? One of the questions I've seen AP ask in the past has been like some version of this going on. What is the net force, or what is the centripetal force on this point mass? Same question. What is the net force? What is the centripetal force? Right? And the answer choices were like spelled out in sentences, and the correct sentence answer was some version of, in this case, it's the horizontal component of the tension. Right? It would be the correct answer. That was an answer choice, right? The horizontal component of the tension. Right? Is that right? It could be total, be a multiple choice question right there. Okay, got that. Right. Oh, next one. Oh, you guys remember a car turning on a road? Right now, if the road was flat, then what force was allowing the car to make the turn on a flat road? starts with an F. Friction, right? Because if there's no friction, you can't actually turn on a flat road, right? Right. But what if, here, suppose one day you guys are designing roads, right? So some kind of traffic engineer, right? Design roads, right? Road engineer. And you're thinking, ooh, well, maybe I'm like way up north and sometimes this road is going to ice over and there really isn't a whole lot of friction. Maybe it's a tiny coefficient of friction, right? So you can't really use the friction to turn. But you could bank the road, right? Right? Do you guys think if you know, say, what the speed limit is, and we're assuming the car's going to go pretty close to speed limit, and you know what is the radius of curvature, right? Like this big old radius right here, imagine like part of a circle, right? Right? You know where is gravity, that in principle you could calculate the angle you have to bank the road to the horizontal so that this car could turn even with zero friction, right? Or minimal friction. Hey, you guys probably all like exited from the interstate, right? And like you're going on one of these loopy roads, and if you're going too fast or the radius is too small and it's really tight turns, like you can almost feel a car like wants to like slip off the road, so you tap the brake, slow down, right? Right? But there is like ideally like some angle so that you could like whip around that road real fast if you want to, right? If it's banked enough, right? So how do you do this? Right. So this could be a longer proof that takes a lot more paper, but I can kind of solve this in like 3 steps. Right. So look. So there's really only 2 forces on this car. Notice I did not draw a friction force. So I'm assuming that maybe the road is like iced over and we're going to turn with no friction at all. So there's only a weight and a normal force from the road. Right? But if you think about it, looks a heck of a lot like this conical pendulum, doesn't it? There's a weight on both of them. There's some force up to the left. I mean, tension pulls, normal force pushes, but otherwise it looks pretty identical, doesn't it? That looks a lot like that. Right? A lot of similarities, right? This angle is this angle here. Oh, you know what? So I meant to ask you, it kind of helps answer this question, solve the question, is if you're the driver of this car, you're like, whip around this curve. At that moment right there, do you feel really light, really heavy, or the same weight as normal? Heavy. I bet you're gonna feel really heavy, right? You feel like some extra force. Feeling those G's, right? Which is a hint that this normal force is going to be larger than the weight of the car. And I drew it that way. Basically, the normal force is larger than the weight, right? Now, normally for inclines, usually your first idea is, well, maybe I want to introduce a Cartesian system that runs like parallel and perpendicular to the surface. That's normally what I tell you, right? You won't actually do that for this one. I mean, you could solve it that way too, but here's the easier way to solve this, right? Is think about this Cartesian coordinates actually aligned to gravity, right? Just like usual, right? And we're going to split this normal force into components. Say, well, this normal force is doing 2 things. It's holding the car's weight up, so the car's not moving up or down, right? You guys see this component of the normal force balances with the weight, right? The other thing it's also doing is it's providing a horizontal component that's acting as a centripetal force, right? You guys see that too? Right. So you got a nice right triangle here. This angle is this angle, right? Got a nice right triangle. Right. This vertical component balances the weight, right? And this horizontal component is the net force, which acts as mv squared over r, okay? Which is got to tie everything together. Okay? So I got this expression right here. Now, because 2 legs of a right triangle have a what kind of relationship with each other? Sine, cosine, or tangent? The 2 legs. It's always what? Opposite and adjacent is tangent. Yeah, it's got to be tangent. Okay. So you could say something like tangent of this angle is equal to this leg, you could divide by this leg, right? Or you can rearrange it and say, if I knew what this leg is here, adjacent to the angle, and multiply by tangent of theta, that will spit me out the opposite leg, right? Which is exactly what it said right here. Take this leg, which is equivalent to the mg, and that comes from the sum of the forces on the y goes to 0. I cut through a few steps here, kind of simplified this, but you guys see where that's coming from? Like, kind of step back, big picture. I only listed like the really critical steps on this page, right? This is equivalent to mg. Take that, multiply by tangent of this angle, it'll tell you this leg, which is mv squared over r, right? You guys see that? Take the mg, multiply by tan theta, they'll tell you mv squared over r, okay? If you wanted to write out like FRQ style, you would put some more steps in the middle, right? But right. Take that algebraic rearrangement, you can get this right here. And now if you know what the speed limit is, so, okay, I think the car's probably gonna go about that fast. I know what the radius of curvature is. I know what Earth gravity is. I can solve for the angle I have to bank that road. Right, guys, that you did. Right. Again, a lot of commonalities with this too. Right, I bet you could do something similar here too. Just went a different way with that one. Okay. All right. So plan all those ideas, stuff you should be able to solve there. And let's look at some of these textbook questions. Now, different textbooks organize this info differently. Your textbook actually does about what AP did. So this is all in chapter 7. Like the first half of chapter 7 is rotational type motion, got some kinematic rotation, got some centripetal force going on, right? And then later on in chapter 7, they talk about universal gravitation. Okay, so we got it all here. All right, so let's going down the line here. Number 5, Dennis drill starts from rest. Right. Oh, already they told you kinematic value. I might see something like initial angular velocity is equal to 0 radians per second. It's right there. After so many seconds of constant acceleration, turns at a rate of so many revolutions per minute. RPM, revolutions per minute, that we're gonna have to convert at some point, right, to radians per second. Find the drill's angular acceleration, and then what angle in radians did it turn during this period, right? Oh, that sounds like an acceleration and kind of like a distance, right? Kind of, right, but angular. Right, so number 5. So I'll say given, right? Let's put all our givens on the board. Right? They told start from rest. So I got 0 radians per second there, initial angular velocity. They told us the time period, maybe I'll do delta t, or you say t, that's fine. Right, time period. They said so many seconds. I'm going to change it for the notes just so you guys have another example. Let's have like, how about 5 seconds? 5 seconds. Right? It goes up to so many radians per, or sorry, revolutions per minute is what they gave you, right? So that is an angular velocity. It's just in these funny units. Let's have mine be, how about 3,000 RPM, revolutions per minute, something like that. Okay, right. No, really, yeah. One of the first things I want to do is convert that to radians per second. You guys want to do that? See if you can stay a step ahead of me. See if you can beat me to how many radians per second is that equivalent to? Right. Omega final. So 3,000 revolutions per minute. I know every 1 revolution is how many radians? 2 pi. Like circumference equals 2 pi r, kind of do, right? 2 pi radians in 1 revolution equivalent, right? And what's the next step I should do? What per what? Yeah, 60 seconds in a minute, right? Does the number 60 go on top or bottom? Bottom, 60 seconds, 1 minute, so that I got some radians per second going on. There's my radians per second right there, right? That's it. Right. So 3,000 RPM times 2 pi on 60. I'm going to go with omega final is, look at that, 314. Is that, that's an exact multiple of pi. I didn't do that intentionally, but okay. I guess that's kind of cool to see, right? That's like pi times 100, isn't it? 314, that'd be radians per second. Right? Or you could say 100 pi if you wanted to. 100 pi, how about that? All right, yeah, let's look at a little tax VV checklist, except I'll do the rotational version. Right? So I know got 0 radians per second there, and I got 100 pi radians per second going on there. And I know this all happened in this amount of time. Your textbook likes to do 3 significant digits. All right, you get, hey, look at that. That's 3 kinematic values. So I can solve for the angular acceleration and also the angular displacement, right? Like in principle, I could get both of them. Right? Right. Now, what's the best way to get there? Which one do you guys want to use? First, second, or third? It's the fastest way. Second one? Yeah. I like the second one too. Okay. Here's why. The first one, look, has 2 unknowns in it, which means you can't use it by itself, right? The third one, same problem, 2 unknowns, right? Now, could you use the first and the third, like system of equations with each other? Yeah, but that would probably like kill a whole forest. So let's save the trees. Yeah, let's do the second one right here. So let's go omega final equals omega initial plus alpha t. Right, then we can solve for alpha and then just worry about theta later. Omega not 0, so just whatever goes away. Right. Can I say alpha is omega final divided by t then? Some version of that. Okay. It's kind of like the definition of alpha, right? It starts from rest. Right. So that's going to be, let's see, 100 pi radians per second it goes up to, and it does that all in 5 seconds. Right, that's like this many radians per second. Or nope, sorry, that many what? It's 62 what? Radians per second squared. That's right. Radians per second per passing second. That's radians per second squared. Right, which is alpha. That's angular acceleration. Right. So it's picking up that many radians per second every passing second. Okay. The other question we got to figure out is, well, how far did it rotate? Okay. I think we got some options. What do you guys feel like? The first or the third? What sounds better? Third? Okay, why not? Let's do third. Right. Right. So yeah, it could be either one. So you get first or third. So let's go omega final squared equals omega initial squared plus 2 alpha theta. Right. And we should know all these except for theta now. Right. Oh, this number's still 0, so whatever. Just divide by 2 alpha. Would that be true? Theta is omega squared on 2 alpha. That would be. Right. So I go up to 314 radians per second. Okay, square that. Divided by 2 times 62.8. I got per second squared. Okay. In your calculator, make sure you have the 2 and the alpha in parentheses, right? So that the calculator knows to put it all in the denominator. Right? Otherwise, it'll get wrong. So that squared divided by 2 times that 5. That's what's the unit, guys? That's 700 and something. What? What's the unit? Radians. Yeah. Solve for theta. That's an angular displacement. Okay. And then the unit that will naturally fall out of the math, out of the equations, has something to do with radians. In this case, it is radians. It's an angular displacement. Okay. Okay. You guys good there? All right. Check out next one. Number 15. A car initially traveling eastward turns north by traveling in a circular path at uniform speed. The length of the arc is so many meters, and the car completes a turn in so many seconds. Determine the car's speed and what's the magnitude and direction of the acceleration. Okay, so cars going along that curved path right there. Okay. Let's figure this out. 15. Okay, I'm gonna make up some different numbers. Let's say given A, B, C, they said 235 meters. Maybe I'll do like about 300 meters. And they said the time to do that was 36 seconds. Maybe I'll do about 40 seconds. Okay, something a little different. Okay. Right. The car's speed. Well, is speed distance divided by time? Distance over time. That's what speed would be, right? Right. And they told us the they told us the radius. Oops. No, they didn't. No, they didn't. Right. They told us the arc length, didn't they? Right. So let's go. How many meters it went divided by how many seconds that happened in, right? Okay. So it's so many meters per second. Okay. Just eyeballing that looks about 15 or 20 miles an hour. I guess that's not too fast. Oh, what is the magnitude and direction of the acceleration? Okay. Now, acceleration, it's not linear acceleration because the car's not speeding up or slowing down. It is constant speed. The speedometer needles staying the same. Okay. There's an acceleration because it's changing direction. And I'm talking about centripetal acceleration. Centripetal acceleration, I know, is v squared over r, right? That's magnitude. And guys, what's the direction of centripetal acceleration? It always points which way? Toward the center of the circle, right? It always, right? Because if, say, the car slipped, it's like an icy patch. So, wants to fly off like tangent to its path, right? But there's probably friction or a banked road, one or the other, that's holding the car, right? So it's pushing it towards the center. It's allowing it to make the curve. Right? We got V. spit that right there. Right. If only we had the radius. Ooh, the radius. Okay. Right. That's what. Well, we know what this arc length is, and we also know that this arc length is a quarter of the circumference. Isn't that true? Quarter of the circumference. Right. So I know that circumference is 2 pi r. Right. And then a quarter of the circumference, divide everything by 4, is equal to arc length ABC. Right? Remember true? So solve for radius. Right? ABC was so many meters long, equals 2 pi over 4 times the radius. Okay, just times 4 divided by 2 pi. We just real fast because we're going to think it's the bell here. Times 4 divided by quantity of 2 pi. Right? We're getting a radius of like 191 meters. Okay. So finally, centripetal acceleration would be v squared over r. That's 7.5 meters per second. We're going to square that, divide by 191 meters. R right there. Okay. Let's do this real fast. I'm getting 0.29 meters per second squared, and that'd be toward the center of the circle. Right, because centripetal acceleration always points that way. All right, toss your live write-ups in the grade tray. I'll get this checked out for you. All right, you guys have a great afternoon.
Oh, yeah.